Have you ever noticed that if you blow over a sheet of paper, that piece of paper begins to rise? Well, in today's episode, let's find out why. Fluid dynamics, the study of fluids in motion. One thing to keep in mind in our calculations is that we're assuming that the fluid flows rather smoothly, like in case A. That kind of smooth flowing is also known as laminar flow. What we want to avoid is case B, which is known as turbulent flow, as it will increase the difficulty of our calculations. Another new definition is the mass flow rate, which is defined by the change in mass over change in time as the fluid flows through a container. Think about it this way. The amount of mass entering into a tube should equal the amount of mass exiting a tube. After all, we're not creating any matter as it's flowing through. The formula to define that is called the equation of continuity. It starts off with our understanding of mass flow rate. The amount of mass going in must match out with the mass exiting. So let's expand on this. We know that mass is equal to density times volume. So if we change the mass but keep the density the same, there should be a change in volume. So we'll replace delta M with density times change in volume. Next, we know that since volume is equal to cross-sectional area times length, we'll see that as a fluid flows, it increases in volume. So the change in volume is equal to cross-sectional area times the length that's flowing through. Last, we know that speed is equal to distance over time, or the change in length over change in time, so we factor that into the formula. What this tells us is that the change in mass over change in time is also equal to the density of the fluid times the cross-sectional area of the tube times the speed that the fluid is flowing. So we'll replace that here. Another thing to keep in mind is that we're taking it that the fluid is not easily compressible. It keeps its same density before and after. So in other words, density 1 will equal density 2, and the formula will drop down to what you see in the red box. This is the formula provided for you on the AP exam. As for all the math that you see here, you really don't need to worry about it. You just need to know the trends that result in the mathematical formula. You've probably experienced this when playing with a garden hose in your backyard. If you leave the garden hose alone, the water doesn't flow out very quickly. But if you try pinching out the opening, the speed of the water suddenly increases. And it's because you've decreased the size of the opening. Here's our first problem. Let's say that we have two tubes merging together into one larger tube. Using the equation of continuity, what would the formula be? Well, we know that the amount of mass of fluid entering in must match out to the amount of mass flowing out. So mass 1 into tube 1 plus mass 2 into tube 2 must equal mass 3 coming out of cross-sectional area 3. Or we can also represent this by A1 V1 plus A2 V2 is equal to A3 V3. The demo that you saw at the beginning of this video is commonly known as Bernoulli's Principle. And what's happening is that when you have fluid moving very quickly, it results in a region of lower pressure. So as I blow on top of the piece of paper, the air pressure above the piece of paper decreases. And since the air pressure below the piece of paper is still at atmospheric pressure, that's what's forcing the paper up. I know that's a very backwards way of thinking of what's happening, but that's the truth of what's going on. Also, the opposite must be true. If the speed of the fluid decreases, then the pressure will then increase. There is a corresponding formula for this, and it's known as Bernoulli's formula. Let's derive it out together. One thing we're going to keep in mind is that the fluid that is flowing through will be incompressible. That will simplify our calculations. Also, work by definition is force times distance, or force times change in length because we're trying to push the fluid through the tube. So we're performing work in pushing the fluid through the tube, but we'll notice that there's some fluid up above. And because it's up above and gravity wants to bring it down, due to gravity, that fluid up above will perform negative work. But we're fighting against this and we're still pushing the fluid into the tube and we're raising it to a higher elevation. So we're also performing work in lifting the object up. So the total work in moving the fluid from a lower elevation to a higher elevation is equal to W1 plus W2 plus W3. But work is also equal to the change in energy, or in this case, the change in kinetic energy. So 1/2 mv squared minus 1/2 mv squared initial will equal W1 plus W2 plus W3. Next, we'll expand, collect like terms, and it all simplifies down to this equation here. Again, with the derivations, we don't really need to worry about it on the exam, but it's nice to know where this formula came from. Okay, let's tackle this question here. Let's suppose an evil wolf comes by and tries to blow off the roof off this building. To make our calculation simpler, let's assume that this building has a flat roof. Now, the only reason why this flat roof will be blown off is because of that decrease in pressure that we've created above the roof. And that decrease in pressure will result in the pressure inside the building pushing the roof off. We want to keep it a flat roof because then it will simplify our Bernoulli equation, and you'll see that soon. This problem is telling us that we need to have a net difference of 22,000 newtons. So F1 minus F2 must work out to 22,000 newtons to be able to lift the roof off the building. Since it's air inside the building and it's regular air outside the building, the density of the fluid is assumed to be constant. Also, the air inside the building will take it as stagnant or stationary, so the speed of the fluid inside is at 0. And now let's try to figure out what minimum speed is required to lift the roof off. So we take Bernoulli's equation, and as I said, to simplify this problem, we'll take it that it's a flat roof, so there's no change in elevation. Also, since V1 is equal to 0, that's another term we can get rid of. We know that P1 minus P2 is our difference in pressure. And since difference in pressure times cross-sectional area is work, then we know that F net is equal to 1/2 density of the fluid times V squared. We isolate and solve for V, and we find out that the wolf must puff with a speed of 32.9 meters per second, or the gust of air coming out of his mouth must be blown at almost 120 kilometers per hour to lift the roof off this building. So what happens to the pressure when the speed of the fluid changes, such as in this case over here? Now in your mind, you can see that as the fluid flows from a more confined area to one where there's more space for it to flow, because you're keeping the same mass, that means the fluid must flow a lot slower. The equation of continuity can also prove this as well. In fact, if we rearrange it, we can see that there's an inverse squared correlation between the radius of opening versus the speed of the fluid. In other words, as the radius of the tube increases, the speed of the fluid flowing through the tube will decrease quite significantly. Here is Bernoulli's equation. To simplify it a bit, we can see that this contraption is set up horizontally, where there's no change in elevation. That way we can simplify the formula quite a bit. We'll isolate for P2. And what I want you to focus on is what's inside the brackets, this relationship between the initial speed and the final speed. Now in this first case over here, we've already expressed that V2 will be a lot less than V1. So in other words, V2 will have a smaller value. And a bigger number squared minus a smaller number squared will result in a positive value inside the brackets. P1 plus a positive number will give us a value of P2 that's greater than P1. So that's the general trend we'll see here. When the speed of the fluid decreases, the pressure in the second tube will then increase. That means the opposite must be true. If we end up constricting the fluid into a smaller tube, then the speed of the fluid will increase. And this time round, we'll have a value of V2 greater than a value of V1. And a small number squared minus a big number squared will result in a negative value inside the brackets. P1 minus a negative value will give you a decreased value in P2. So in general, when the speed of the fluid increases, the pressure will decrease. Again, you don't need to derive this. You don't need to worry about any of the equations. You just need to know the general trends. One last thing just to keep in mind. When the radius of opening increases, the pressure in the second tube will increase, but the speed of the fluid in the second tube will decrease. Here's a neat little demo that you can try at home. You take 2 straws where you set the top straw just behind the vertical straw, and if you so happen to submerge the second straw in water and you blow over the first straw, you just made your very own air spray can. Want to see the math behind how this works? I'm sure you do. Well, that was an interesting demo. Let's see the math behind it. First thing, we need to elevate the water from a lower elevation to a higher elevation so that there is a pressure head. And to minimize the pressure head, that's the reason why I chose a very short straw. So the first thing I need to do is to figure out what is the change in pressure required to lift the water up by 5 centimeters. Next, we need to find out the speed of air required to produce this negative pressure to draw the water up by 5 centimeters. So the first equation we'll use comes from an earlier video, which is called the pressure as a function of depth equation. So we're trying to find out the difference in pressure required to lift the water up by 5 centimeters. And that difference in pressure, in this case over here, works out to 490 pascals. Next, we use Bernoulli's equation, but we have to think about the fact that we're taking a look at the air through the horizontal straw, the straw at the top, where there is no change in height. And on top of that, the water has no horizontal component yet, so the speed right at the water is at 0. When we rearrange this equation and solve for the difference in pressure, then we can sub our 490.5 pascals as well as our 1.2 kilograms per meter cube for the density of air, and isolate and solve for V2, and it'll work out to 27 meters per second, or roughly 100 kilometers per hour. So that's why I have to blow so hard to make this contraption work. Here's another problem to tackle. Let's say we were trying to relocate fluid from a lower elevation to a higher elevation. Also at the same time, we're going to open up the radius at the second opening, so at point B. And the question is, what will happen to the pressure by the time it exits? So there's two things going on. I'm lifting up a fluid, which will then result in a decrease in pressure at the higher elevation. And number two, I'm opening up the radius of opening, which will reduce the speed of the fluid flow, which as a consequence will increase the pressure again. So the results at the end would probably be closer to 200 kilopascals. But let's calculate it out anyways. One thing to keep in mind is that we have to figure out the cross-sectional area. And since the diameter is at 10 centimeters, that means the radius is at 5 centimeters. And since it's a circle, cross-sectional area of a circle is pi r squared. Using these givens, the next thing we got to figure out is how fast is the fluid flowing at point B. So we need to use the equation of continuity and figure that out. And as you can see, the speed of the fluid decreases because of the larger opening at point B. Lastly, we can use Bernoulli's equation. And after you sub everything in, that works out to 162 kilopascals. So as predicted, the pressure may decrease initially, but then it'll increase again because of the larger opening. Of course, the consequence of this setup is that even though the pressure is restored, the speed of the fluid as it exits out of the opening has now decreased. One last example. Let's say that we fill up a silo with water, up to an elevation of 15 meters. We punch a hole at the 10-meter mark and let the water drizzle out. The question is, how fast does the water exit? For argument's sake, let's say the opening right now is at 10 centimeters. Would it make a difference if we close it off to 5, or if we opened up to 15? Would it make a difference? Well, we'll talk about that right after. Now, there's a long-winded approach in solving this, and you can see it in an earlier video with the links that were attached. However, there is a much faster shortcut. And to solve for this really quickly, avoiding any of the equations we covered in this section, we can just use the conservation of energy approach. Since we know that the water is losing altitude, it's gaining kinetic energy. So the change in gravitational potential energy will result in a gain in kinetic energy. And then when you calculate it out, you'll find out that the final speed works out to roughly 10 meters per second. And this will be 10 meters per second regardless if the opening is as small as 10 centimeters or as large as 20 centimeters in diameter. It won't matter. For more additional review, please check out us.archive.org. There are 2 videos that correlate to this video here. And if you like this video, consider watching the rest of my videos as well. Anyways, that's it for now for this particular chapter. Until our next adventure together.